Okay, in this last video here, we're going to do a few problems, and then we're going to discuss another type of substitution reaction called nucleophilic aromatic substitution. Okay, so we're going to design a synthesis of a way to convert benzene into each of these multiply substituted compounds. And each of these requires a different sort of strategy. We'll look at each of these. What I advise you to do, if you're following this video, is to pause it and try these on your own and see how close your answers are to being correct. So first let's look at this one. How do we convert benzene into this compound? Notice that we have a series of three groups that we need to put on. This one will come on through the Friedel-Crafts acylation. Okay, this from halogenation, and this from the Friedel-Crafts alkylation. Okay, so what's involved in this? First thing to note is that bromine is orthopara to the best electron donating group. It's better to install that one last. Okay. Acetyl is orthopara to the best electron donating group. It's better that we install acetyl after ethyl instead of the other way around. So let's look at the best way to do that. As you can see from this analysis, we're going to ethylate, acetylate, brominate. Okay, so when we do that, we put the ethyl group into a ring that has nothing, as you see here. React this, react ethyl benzene with these two reagents here to do the Friedel-Crafts acylation. This is going to go para. A little bit of it will go ortho, but mostly para. And bromine FeBr3 is going to put bromine here. Remember, ethyl is the boss group. It's electron donating. This one's electron withdrawing. So we're of course going to add orthopara to that. Okay, there's some variants we could have made. I guess using the rules I gave you, technically this would be okay. Oops. Okay, but it wouldn't really be ideal. Okay, because it's unlikely. Usually you get a little bit more para than ortho, but the ethyl is a stronger donor than bromine, so that would be okay. Now, let's look at some other hypotheticals. Let's say we acetylate first. Okay? So we're going to hypothetically consider adding this first. Okay, that's a meta director. We could add this stuff. And no doubt we would get this. But what's going to happen here? This won't work, right? Because the ring is too deactivated. It can't happen. Remember, you can't do any of the Friedel-Crafts reactions on a ring that's less activated than a halobenzene. So this is a variant that you could not do. Okay, let's look at the next problem. But the route you see here in magenta is by far the best one. Okay, how do we make this? What are some things to note? Okay, so let's remember a few things here. This group is going to come from a side chain oxidation, right? Okay. So before the side chain oxidation, it's an alkyl group and electron donating. After the side chain oxidation, it's a carboxylic acid and electron withdrawing, or meta-directing. Okay? So notice how everything here is either ortho-apparent to COH, means that we want to keep the alkyl group intact while installing these other things. We want this to be an alkyl group and then just put things in ortho-para to it. Okay, the best way to do this is to make ethylbenzene or any other alkyl group that's capable of doing the side chain oxidation. You just don't want a T-butyl group here. Since you usually get more para than ortho, this would be the best reaction to do next. Then we would want to add chlorine and the nitro group. These two reactions, let's just give them all names. We'll call them step A, B, C, and D. C and D are interchangeable. No problem with reversing them. Okay, and we'll call this last step E. Okay, so where could we screw up? Well, you could screw up by doing this too early. Okay, so let's do step E right here. Okay, we'll just draw a circle there. Now, whatever we do next is going to place carboxylic acid and whatever comes in a meta direction. And notice that if you look at this, there's nothing meta to the carboxylic acid group. So you've got to wait to oxidize the carboxylic acid group. It would probably be okay to oxidize it here. No, you could not oxidize it here. Chlorine is still an ortho-para director, so you have to have this outrank chlorine all the way throughout the synthesis. So this, shown in magenta, is one of two correct answers. The only variation on the correct answer is that C and D could be interchanged, but none of the other steps really. Okay, I guess you could say you would do C first, right? But I like the synthesis that you see before you because, again, you want to put your para group first since you usually get more para than ortho. Okay. Let's look at electrophilic aromatic substitution in higher benzenes and in other aromatic rings. So here's naphthalene. Naphthalene, right here, also undergoes electrophilic aromatic substitution. When naphthalene undergoes electrophilic aromatic substitution, it produces mostly the one substituent and less of the 2-nitro-naphthalene. Okay, what's the reason for this? Okay, let's consider the hypothetical carbocations. Okay, so we can, as always, we draw 3 of them. Here's the first one from attack at the 1 position. Here's the next one from doing the allylic resonance structure and 1 resonance structure again. Notice that when we go from here to here, it's not so great, is it? Because we break aromaticity. Okay, so this one, it doesn't really have, it's messed up the aromaticity in the other benzene ring. Alright, when we add to the 2 position, we initially get this. And then we get another one that's also has the aromaticity broken. Right, this isn't a 6-pi electron ring anymore, and both of these resonance structures have the benzene ring structure, or have torn up the benzene ring in the other ring. Okay, so the top one's better because of the 3 resonance forms. Only one messes up the aromaticity in the other ring, but when you attack the 2 position, as down here, 2 out of the 3 resonance forms are not really all that great because they've broken the aromaticity in the benzene ring. Okay, let's look at heterocyclic aromatics here. And I'm going to use furan as the example, but everything I say about furan goes for thiophene and pyrrole also. Okay, so when you do electrophilic aromatic substitution on these types of systems, they're actually quite activated. You can think of this as being an ether and this as being an amine. You see the product from attack at next to the heteroatom. This is actually called the 2 position, and this is the 3 position here. This is the 3 isomer. Okay, so you see the 2 substituted furan derivative and not the 3 substituted furan derivative. And why is this? Well, both of them look pretty good resonance-wise. When we attack the 2 position, as you see here, this is our initially formed carbocation. We can write a resonance structure, and we can also write yet another resonance structure there when you consider the lone pairs. Okay, so we can write 3 good resonance forms when we attack the 2 position. Okay, when you attack the 3 position, this is your initial compound. You can draw a resonance form with the ether, which is pretty good, but you can't draw any of the allylic resonance forms. So, because you can write more resonance structures for the attack at the 2 position, this tends to be the predominant pathway observed. Okay, let's do a little problem here before we move into nucleophilic aromatic substitution. I'm sorry this one didn't occur earlier, but this is a classic type of problem. Rank these compounds in terms of their anticipated reactivity toward an electrophile. i.e., how reactive are they in electrophilic aromatic substitution, or how activated or deactivated are they? We're going to give the most reactive one here as number 1, and the least reactive is number 6. And we're going to use nitration as the sample reaction. We could have really used any of the reactions as a sample reaction. Probably we couldn't use the Friedel-Crafts, however, because a couple of these are actually unreactive in the Friedel-Crafts reaction. So we'll get some ties if we did the Friedel-Crafts reaction. Scoreless ties. Okay. Alright. So let's look at what we have here. we have electron withdrawing group, weakly electron withdrawing, have electron withdrawing group, strongly electron withdrawing, and weakly electron withdrawing. So these two rings are deactivated. Benzene, of course, is unactivated. It's the standard by which all the others are set. This has got an electron withdrawing group, a strongly electron withdrawing group at that. And this one also has a strongly electron withdrawing group. This has the only electron donating groups we have are the same one, and they're all strong. Okay, they're all equal, of course. EDG, EDG, and EDG. Okay, so it's easy to find the most deactivated, right? That's this one right here. The one that has two strong electron withdrawing groups. This one, not as deactivated. This is number 5. And this is number 4. It's also deactivated relative to benzene. And benzene is number 3. So how do we choose between these two? Well, it's important to note that in this one, the hydroxy groups cooperate. They're wanting the incoming electrophile to attack the same position, whereas here, they're opposing each other. And if we look at what happens here, let's say we're going to have this react with the what we know to be the attacking electrophile NO2+. Okay, I'm at the edge here, sorry. Alright, there we go. And of this carbocation, you're actually going to see the positive charge delocalized here and here. So the carbocation you get is actually stabilized by both of the OH groups. Sorry, OH. Okay, so the carbocation is stabilized here and here, whereas only this one can get, when you attack, no matter what position you attack in this one, you can't get resonance stabilization at by more than one of those OH groups. Okay, so the net answer is that the meta-substituted dihydroxy compound is number 1. This is number 2, 3, 4, 5, and 6. Okay, let's look at the last type of reaction, and this is nucleophilic aromatic substitution. This is not quite as important as electrophilic aromatic substitution. For one, we already have to have a halogen on the ring, and we're going to find that most benzene rings actually don't do this reaction. Okay, recall in the discussion about the SN2 reaction that this is something that we can't use in the SN2, right? We can't do SN2 at sp3 carbon. But there is one exception to that rule, and that's when you have halogens on benzene rings and you have really good electron withdrawing groups in the ortho and para positions relative to the halide. When you have this type of compound, you can do the electrophilic aromatic, the nucleophilic aromatic substitution. For example, reaction of this with methoxide ion very readily produces this compound here. Reaction with the nitrogen nucleophile readily produces the amine derivative. Okay, let's look at the mechanism and some of the trends in nucleophilic aromatic substitution. It's not the SN2. We'll see that when we look at the mechanism. And we have a very strange ordering here. The best X to have is fluorine, better than chlorine, better than bromine, better than iodine. Remember that all throughout this class, fluorine has not been very good at anything, right? It's been either too reactive so we don't use it, or it's been not reactive enough so it doesn't participate in things like the SN2 and the E2 reaction very well at all. But in nucleophilic aromatic substitution, fluorine is actually the best one. Okay, so here's the proposed mechanism for nucleophilic aromatic substitution. What happens here is that we add the nucleophile to the ring and we get an anionic ring, and we can write resonance structures like we did before, switching the position of the double bond and the negative charge, just like we did with carbocations in electrophilic aromatic substitution. And we find that the negative charge is delocalized ortho and para to our halogen. Okay, remember how we said it was not good to put a positive charge right beside a nitro group because it's electron withdrawing, but it's really good to put a negative charge beside a nitro group because a nitro group is electron withdrawing, and this anion says that you have too much electron density, so you want to get rid of some of it. Okay, and we can even write a resonance structure. If you consider that carbanion intermediate, and so a carbanion next to a nitro group, that's not a very neat nitrogen, is it? Has that resonance form, right? Okay. This is the slow step, the addition. And this is where fluorine shines, because fluorine is the most electron withdrawing. There's more of a partial positive here when this is fluorine than in any of the other systems. Okay? So this reaction happens fastest for fluorine. The carbon-fluorine bond is quite strong and it's hard to break, but it breaks in the fast step, so it's not seen as part of the rate equation. Okay, and that explains the preferred use of fluorine in these reactions. Okay, let's do a classic question here. Rank these as to their relative reactivity to sodium methoxide, a typical nucleophile. Sodium methoxide is just the nucleophile that we've shown here as an example. You could have used several of them. Rank the most reactive as number 1, the least reactive is number 5, and place number 2 through 4 wherever appropriate. Okay. So we're looking for two factors here. One, we want as many electron withdrawing groups in ortho and para positions as we can get, and fluorine would be better than bromine. Okay, so here we go. EWG, EWG, ortho and para. EWG, EWG, ortho para, electron withdrawing group para, and here EWGs are both meta. Okay, so fluorine is best, and it's better than systems where we have a bromine. So we're going to choose the one that's got fluorine and the ortho and para groups in the right position as number 1. This is going to be number 2. It's not quite as good because it's bromine, but it's still pretty good. We'll choose this as number 3 because it has a group para. These last two, 4 and 5, I'm not sure that either one of them are reactive to methoxide, but we'll just put them down as the one with the electron withdrawing groups as more reactive. Okay, so this would be the way the ordering comes out. And we'll just say there's a little bit of uncertainty as to that one. Okay, I think this is the end of our slideshow here, so I'm going to just stop it. Okay?